Хорошо. Nice. It's recording now? Good. So
Mhm.
many algorithms tend to define this bounding box using the center point, the coordinates of the center point. So basically the X and Y coordinates of this pixel, plus the height and width of the object. So we can see here that for object detection, we're going to be describing, or we're going to be predicting a variable amount of objects. So if the image has 5 objects, we're going to have 5 output bounding boxes and their classes. And if it has 2, we're going to have 2. So this means that the architecture of the model should be either generic, so it should take in consideration to output a very large amount of bounding boxes, or it should be creating the bounding boxes in a recursive manner, right? So basically, either we just say for each point of this original image, we might attribute a set of bounding boxes. Hence, we will allocate, for example, an array inside the RAM for 5 pixels in each, for 5 values for each pixel in here. So this would be one way of doing things. It would consume a lot of memory, but it's possible. Another way would be to just go through the image, and wherever you find a new object, you create the what are they called, the bounding boxes and the classes. So basically, there are 2 main ways of doing this, either by allocating the space for the bounding boxes before starting, or we just recursively do this again and again. Some of the applications are vehicle counting. We described these things yesterday, facial detection recognition, and parking lot monitoring, right? We saw that the basic model that we can use is a sliding 2D CNN. So basically, we take our 2D CNN and just slide it through the image and classify different patches of the image. We saw that this idea is not very feasible, because if we're going to slide the image pixel by pixel, we're going to have lots of convolutional operations, and that's going to take a lot of time. So we decided to simply perform the same task, but on a smaller images, and augment or only focus on this area that we're interested in, while we are improving or augmenting the size of the image to the original size again. We saw that there was another idea that could be used, which is to, instead of putting the classifier on every single part of the image, we just put it on areas of interest. So these areas of interest are selected using an algorithm called selective search. We will go in depth about selective search and how it works. So this is just a simple algorithm which tries to combine neighborhood pixels, so basically neighboring regions, based on a similarity metrics, right? We saw a very important notion, or a very important metric yesterday, called intersection over union. And this is the equivalent of what accuracy is to classification. So basically, the intersection of a union describes how close or how similar 2 bounding boxes are to each other. So we can see that the higher the intersection is, the better the overlap, or the better the similarity is. And the higher the union is compared to the intersection, the worse the similarity is. We saw that one big problem with this model is called, it's overlapping bounding boxes. And we proposed a new algorithm, or an algorithm for solving this problem, called non-maximum suppression, which focuses on finding the bounding box with the highest confidence, and then removing everything, or removing the other bounding boxes that overlap with it greatly. So for example, in this case, we selected the middle bounding box, and then we started searching for other bounding boxes that overlap significantly with our chosen bounding box, and then removing them from the predictions. The details of the algorithm are here, but the algorithm is completely simple and very predictable. And then we started speaking about the first algorithm for object detection, which is RCNN. So this was the beginning of a new family of different models. RCNN stands for region-based convolutional neural networks. And what it does is it simply takes an input image, feeds it to a search algorithm, and then the search algorithm proposes different regions inside the image, and the CNN, basically the classification part, is what you are already familiar with. So basically, we take the region, we classify it, and if we find something interesting, we will go to, let's say, accurately or change the coordinates of the object within that region. The selective search algorithm in small words is the following. So we basically select an initial subsegmentation inside the image, and then we iteratively continue grouping the neighbor segments together if they are similar. So for example, let's go back here. Let's start by saying that this is a segment and this is another segment. If the pixel values are the same between these two areas, then we will merge them together and consider this as just one area, right? So this is basically the selective search algorithm in a nutshell. We will go into detail a bit later on. Some of the problems in RCNN are, first, the big problem is, the small problem is, let's start with small problem. So the small problem is the selective search. So selective search algorithm is a bit heavy on calculations on the CPU. So basically, it proposes 2,000 regions inside the image. The proposal itself is not the most expensive part. So the most expensive part is the fact that RCNN sends each region on its own through the convolutional neural network. So this operation of proposing 2,000 regions is not very heavy, but when you take every region and send it through the CNN on its own, this operation tends to be very computationally expensive. So we can think of it as 2 seconds going to the, selective search algorithm, and then 45 seconds going to sending each one of these regions into the ConvNet, right? So in FastRCNN, they solved the second problem, or the problem of sending every region through the CNN again and again. So this sending 2,000 regions to the CNN is a very difficult task, and it takes a lot of computations. FastRCNN, this FastRCNN just added a small, very important feature, which is we no longer send every region through the CNN, but we send the image as it is, as a whole, through the CNN once and get the feature map. Later on, we still apply the same algorithm of selective search, and the selective search would propose to us different regions inside the image. What we will be doing is, instead of feeding this region through the CNN again, we will not do that and only find the corresponding area of this region inside the feature map. So basically, if this was the region that we're interested in, this is its corresponding area in the feature map. We resize it a little bit or apply ROI pooling on it, and then just send it through different classifiers and bounding box regressors. Another very important thing in RCNN that was added, or FastRCNN that was added, the fact that these two neural networks are done they both share the same fully connected layers in the beginning, right? So previously in RCNN, both, so basically the object detection or the bounding box regression and declassification had separate fully connected layers, but now they share some of the fully connected layers in the beginning. And then of course, the final layer is different for each one of them, right? Now, a very good important question would be, what is ROI pooling layer? So we understand what's happening here. We take the image, send the whole image through the CNN just once, and then get a feature map, apply the, region selective search to get different regions inside the image, find their corresponding area inside the feature map, and then sending it through the classifier, which is in ROI pooling, followed by some flattening and fully connected layers. This is what's just wanted to show in more detail what's happening. So basically, we have an image. We use the selective search algorithm to propose some regions inside the image. And then what we do, we map this area to where its feature maps should be located. So for example, you know that, for example, if we take the convolutional layers and convolutional kernel on this area, it will give us 1 point in the feature map. And then the same, we go on and doing the same again and again and again. So we would be kind of looking at it in the reverse. So basically from that point in the feature map, what are the pixels that were used to generate this point? And so basically this is the architecture. We take a region, find where it is on the feature map. So we do not send this region again through the CNN, just find it in the feature map and send it through ROI pooling and the fully connected layers for classification and bounding box regression. Problems of, okay, I think the slides are not updated yet. I should have a slide here about, well, the biggest problem of fast RCNNs now remains, which is the region proposal algorithm. So the region proposal algorithm is still being used. It's not dataset specific. It still consumes a lot of computations on CPU and it's time consuming, right? So the idea here would be to keep everything the same in fast RCNN, but propose a new algorithm for detecting the regions. And we can see here the difference in, or the great difference in the training time and the great difference in the inference time between RCNN and fast RCNN. The next algorithm that we will be seeing is faster RCNN. And in this diagram, we will just see the bigger picture, and then we will go in more depth about every single step in this pipeline. So basically, we take an image, send it through a backbone. So this is the VGG backbone to generate its feature maps. The backbone will be shared between the two steps of first proposing the regions and the second step, which is just a fast RCNN network, right? So the second step, you guys are already familiar with the step, so you know what's happening here. We take the image, send it through the backbone, we get the feature map, and then once we have the region proposals, we find the corresponding area or the corresponding, what is it called, feature map inside, yes, the corresponding feature map values inside this feature map, and send it through our shared fully connected layers, and then just send it through the classification and the regression. So this part is the same thing as fast RCNN. What changed is that we will be using something called as region proposal networks. And region proposal networks are like the equivalent of selective search, but using only neural networks. So basically, this operation can be done on GPUs, and usually any operation that's done on GPUs tends to be faster than those who are done on CPU, right? So the algorithm in just small steps again. So basically, we take the image, we send it through the backbone, we get a feature map of the last layer. No, this is, yes. Let's just skip this one and get to the region proposal networks a little bit first, and then we go back there. So here are the, this is the architecture of the region proposal network algorithm that is being used. We take the image, we use the same backbone for fast RCNN to extract these feature maps. And then from the feature maps, we will be sliding a new set of, let's call them anchors. So we will be sliding a set of anchors through the feature map to try to detect whether this point in the feature map corresponds to an object in the image. So to see this in more detail, so what we will be doing, we will take some, for example, a point in the feature map, find its corresponding location in the image, and then apply a set of anchors on this image. So these set of anchors will be just, let's consider them just like cropping, right? So we will basically crop the image onto only this region and be interested in this region, whether this region contains an object or not. So these are what anchors are. You can see that anchors come in different sizes and different ratios. The first type of sizes is the large sizes, and these are responsible for detecting large objects. We find that the green ones are a bit smaller. So basically these are the medium size anchors, and they're responsible for detecting medium size anchors, medium-sized objects. And then we have the final set of anchors, which are the small anchors that detect the small objects. Each set of these anchors usually is either a rectangle, which is horizontally made, or a rectangle which is vertically set, or a, what is it called? So basically either this shape or this, so there's a rectangle. Square, yes, thank you. So basically either a rectangle like this or a square like this. So basically to be able to see different types of objects in different scenarios. Of course, these anchors are not perfect. Still, you can, if you want, fine-tune the shapes of the anchors in your own model. But usually this step is either too much computations for you, or you can just use the PPYOLO architecture, which proposes a learning of these anchors for your own data set before going to learn the model. So for most of the models, we will be using the anchors dimensions, and the anchors, these ratios will be preset for you guys before the training. To just see how RPNs really work, let's imagine the following scenario. So basically, we will have a sliding window, or just a sliding point, let's call it sliding point, through the feature map, through the convolutional feature map, where we will be applying all the different anchor boxes. So remember, we have 9 anchor boxes in this area. Basically, we will put a point in here and surround it with 9 different anchor boxes for the different shapes that we have. Each one of these anchor boxes will be doing some fully connected. So basically, it's just we take these values, multiply them with some weights, and then add some bias, send them through some activation function, and then they will be going for making the classification and the bounding box regression. It's important to check the values in here. So for example, in this section, we have 2 times k scores. So the k comes from the number of anchors. The 2 comes from the fact that we are trying to detect whether there is an object or there's no object. And so basically in this stage, we are not trying to detect the class of an object. We're just trying to detect the presence of the object. And then the 4K coordinates system is just trying to optimize the coordinates of the object inside this anchor box, right? Yes, just to put it everything again in perspective, first step would be to train an RPN to detect the, what are they called? The region proposals. And then using the same VGG network backbone, we will be extracting the feature map, or we'll be extracting some regions of interest inside the feature maps and sending them through ROI pooling, flattening, and then just a couple of convolution, a couple of fully connected layers to perform the classification and the bounding box regression.
May I ask one question, please?
Yes, of course, go ahead.
About the first part, it's about the region proposal, because we, as understood, we have like a classifier and aggressor in this part. Classifier says where is the object or no, and aggressor, which give us coordinates. Yes. And my question is, why we have regressor in both parts, like in the region proposal and the classification? Why so? Why need two times to go for regression?
That's a good question. And the answer would be, in this case, the coordinates that you might have gotten are quite generic. So these are the coordinates of any type of object, right? So it might not be very optimized for every single type of class that you have. Basically, the bounding boxes that you will be using here, these are the bounding boxes that you will be truly using. And in most cases, these bounding boxes are better at predicting the exact location of the object. And again, if you're familiar with some architectures of CNNs, remember the architecture of inception, as I remember. So basically, we have the classification step happening at several parts of the neural network. And this allows you to train better weights, right?
Okay. Yeah, you're right. I understood. Thank you.
Хорошо. So basically, again, for the VGG network, it's shared weights between RPN and your fast RCNN network. And basically, just to put everything in summary, we have RCNN, which takes a region proposals algorithm, which is such as selective search, for example, and sends each one of these regions that are proposed by the algorithm through a deep convolutional neural network, and then that goes through a bounding box regressor independent from another SVM object classifier. So basically, why use an SVM object classifier and not just train a normal object classification or image classification algorithm? They said that in this case, SVM gives better results. So basically, the loss of SVM is better than the loss of cross entropy in this case. But then you see that they quickly just abandoned this idea as the softmax loss gave even better results. Fast RCNN was an improvement over RCNN, which kept, again, the selective search algorithm. It's still there, but instead of sending the each region through the CNN again and again, only thing we do is we take the image, send it through the CNN once, and then we find the equivalent, or we find the mapping of that region that's proposed by selective search. We find its mapping inside the feature map and just send the feature map through ROI pooling and a joint classifier and object detector at the same time, and object bounding box regressor, right? Faster RCNN was an improvement of fast RCNN, and it only kept following. So basically, we have fast RCNN here, but we only changed the step of region proposals by using an algorithm that is, or by using a neural network that is fully trainable and kind of specific to your own data set. So now we both get the increased accuracy or the increased performance, since the step of region proposals is now data set specific, and we get the increased time performance since the calculations now are being done on GPUs and they can be parallelized together. So basically, here, so for example, here we can parallelize the computations again and again. And for the different anchors, we can think of them as just a batch that will be sent to this neural network. So basically, the computation here is a little bit expensive, but can be optimized very easily. So far in this lecture, what we have just recovered, we have recovered concepts of object detection. What is, we've seen what is intersection of reunion, what is a non-maximum suppression. We've seen what RCNNs are, fast RCNNs are, and faster RCNNs, and the improvements between each one of them. So we've seen that RCNNs was just a basic convolutional neural network that's using a selective search algorithm. So basically, it gives it some proposals, put CNN on that, and then try to classify and find find better coordinates for the object. Fast RCNN kept the same searching algorithm, but just removed the step of sending each region through the CNN, but only keeping or only sending the image once through the CNN and finding the corresponding region inside the feature map, sending that feature map through an ROI layer, ROI pooling layer, and sending the rest through flattening and convolutional layers to do the classification. We've seen that faster RCNN is the same thing as fast RCNN, but with removing the selective search algorithm and replacing it with an algorithm that is based on neural networks, and it's called feature pyramid networks. No, RPNs, region proposal networks, sorry. So feature proposal networks are something else. So region proposal networks, which slide a set of anchors through the feature maps and try to predict whether that anchor yes corresponds to an object in the image or not, and try to improve the values of the proposed regions again. So this is what we have seen so far. Next step would be to speak about Detectron and the YOLO family of models. Do you guys have any questions so far in here? I don't see any questions in the chat, so yeah, go.
Actually, we didn't cover Mask RCNN, but you talk about it.
Yes, Mask RCNN will be covering it kind of in this section. So that's why I kept it here.
Okay.
Yes.
Could you please again explain why we use SVM object classifier in RCNN instead of softmax, for example?
In the first RCNN.
Yes, yes.
That's a great question, and I think the good answer would be to check the paper and compare the results. So basically, it's only a matter of results. And let me share the paper with you guys. Here we go. Oof, how do you share? Yeah. So basically, this is the fast RCNN paper. We will be using this one instead of the RCNN paper because they discussed this concept in detail. I think it's either in this paper or in the faster RCNN paper. I will check. Are more proposals always better? No. They discuss it in this. Yes. Does using SVM classifiers outperform using softmax? So in their first initial model, so basically what they did was RCNN uses the soft, let's just read it quickly. So fast RCNN uses softmax classifier, the one that we usually use for classification, instead of the one which is used in RCNN, which is training a one versus rest linear SVM, as was done in the RCNN. And this is another architecture, SPPNet, which is an improvement over RCNN, but it was quickly forgotten. To understand the impact of this choice, so basically here are a couple of numbers. And in here, you can see that softmax kind of improves over using just an SVM in large objects. We can see here that, yes, so for example, in this case, again, it outperforms it drastically. And for these small objects also, it outperforms itself drastically. A very interesting finding was that, for example, here, RCNN outperforms fast RCNN on medium and small objects, but that's not what we really, what we are trying to answer here. The question exactly is whether SVM is better than softmax for fast RCNN. And the answer was, in this case, fast RCNN with softmax always improves over SVM one versus all classifier in the case. So just so I understand correctly, are you familiar with what we say with one versus rest SVM? Or one versus all? I think you have seen it as one versus all model. For the person who asked the question?
Sure, sure. I guess I understand, but at the same time, one was rest.
So do you understand what the SVM
like
is?
to
Right?
class
So,
classification. You'll predict either it is this sample of this class or not of this class.
yep. So basically, remember what SVM does. So basically, SVM takes, for example, a set of values, integer or float values, and tries to give you the classification, right? Same thing will be done here. We will take the output of the final layer and consider it just as, what is it called, values, right? So this is your input for the SVM, and train SVM linear model on these, on the final output of the final layer, right? So basically, this is how do we use it? How do we make the classes? So basically, we will be training different SVMs for every one of these classes, where we will be doing one versus rest situation. So there are either one versus one situation. So basically, we have a dog versus cat, a dog versus tat, or we have a situation where we have dog versus all the other classes, cat versus all the other classes. So this is one versus all and one versus one differentiation. And yeah, why did they stop on using SVM as the final classification of their model? It's just a question of accuracy, or a question of improving the results, mean average precision. We'll speak what mean average precision is, but we can think of it as accuracy for now. And the whole question was just improving the results, right? So do not compare these results, compare with these results. So this is softmax, this is SVM on the same model, fast RCNN. Did this answer your question?
Sure, thank you.
Nice. Another very important, yes.
You said that you want to go through the Roy pooling one more time, like or in deep. Will we do it?
Yes. 1 second, I will answer this question. Our answer, yes. Are more proposals always better? So this is a very important question in this case. Again, as we said, so kind of, I just told you guys before that FastRCNN uses a selective search as part of it. So what they did is they kind of abandoned selective search algorithm in FastRCNN and kept the algorithm of FastRCNN on 2 steps. So basically, the algorithm requires an input image and requires the region proposals before the algorithm of FastRCNN starts. So in most of these, so for example, why wouldn't you find good resources in the paper about how do they do the region proposals? It's because they expect the region proposals to be input to their model. Let's see it here. Yes, so basically the input of the model of the RCNN architecture completely is an entire image and a set of object proposals. So how do you give me these object proposals? I don't care. What their FastRCNN architecture says is just about the rest of the architecture of sending the image through the convolutions and then just taking the feature maps of these regions and sending them through ROI pooling and the rest of the features, right? This is a small comparison of different algorithms that they have used instead of selective search and their output. So basically here we can see selective search by default, selective search plus another algorithm, as selective search replace dense, and then there's this another algorithm and another algorithm, and this is the recall of selective search. So basically, the more proposals selective search will be giving, the better its recall will be. So basically, it will just give you all types of objects inside your image, right? So we see that the more proposals as selective search gives you, its personal recall increases and increases. And now what interests us is the following, right? Yes. So here we can see a selective search on its own, adding more values or adding more proposals does not really hurt the performance of FastRCNN. It's kind of gets to its maximum around 3,000, yeah, around a couple of thousand proposals, but it doesn't really influence it that much. Of course, once you got to proposing numbers such as like 10 in like, what is it called? So there's 1,000, 10,000, hundreds of thousands proposals per image, then it kind of gets to decrease a little bit. So this is just a comparison. These are like some very important questions that they covered in the end of their lecture or in the end of their paper. Now, I hope that you guys can have a small or a overall idea on how these different architectures work from RCNN, FastRCNN, and FasterRCNN. These algorithms just to understand the steps of evolution of object detection and its architectures, but all these algorithms are kind of old school algorithms, and yes, exactly, you are correct. So in most of the cases, you will not be using RCNN. You will never be using FastRCNN. FasterRCNN, definitely, you're still going to be using it. And yes, yeah, of course, MaskRCNN also is still going to be used. One of the algorithms that we'll be training in the lab will be FasterRCNN based, right? Now I would like to share another thing, just some cool thingy. I think it's here. No. No. Yes, this is okay. So right now we will just go a little bit into more detail about an algorithm called, or about the step of RCNN, fast RCNN, which is called ROI pooling. So far what I've described, ROI pooling, is just another equivalent of max pooling that resizes every kind of input to the same size. I think, no, not this. This one. It's the same one? Yes, this one, right. So this is a very cool resource that I just found, and it has some very cool visualizations. The most important visualization that I liked was the following. So here we are applying a ROI pooling to a, well, this is a point inside the image, right? You see, ROI pooling takes any type of input and performs a max pooling on it. So if, for example, we have, we want just a 2x2 output, what we will do, we will take any type of size that we want and try to split it in a manner that gives us 2x2 boxes. So in this case, here we have 2x2, here we have 2x3. If we were going to apply this algorithm on, let me add some drawings. Yes, if the algorithm was going to be applied on this region, our proposals will be different. So in this case, we have 1, 2, 3, 4, 5, 6, 7 in this sky, and 1, 2, 3, 4, 5, 6. Yes, so basically we will split it like this and like this. Can you guys see it? So here we will be taking the max pooling or the maximum value in this area, put it in here, the maximum value of this area, which is 3x4, putting it in here, the maximum value of this area, putting it in here, the maximum value of this area, and putting it in here. So this is just kind of an.
And how does should we choose these areas? One area is smaller, one area is bigger.
Yeah, it doesn't really matter. So basically, it tries to split the height of the object or the height of its interest by the height of what it wants. So basically, here we have 7 divided by 2. This gives you 3.5, right? So basically, this is the height that we were given. This is the height that we want, right? Let's make a different visualization just to see this example.
I think here is like a very simple calculations. If the algorithm can like divide it equally, the regions,
Yes.
well, it will divide it equally. If not, he will like try to find more numbers and just do it how he can.
Let's make a drawing here and calculate it manually, right? There you go. And what I want is to apply ROI pooling on this area. And I want it to fit in an area of like this, 3x2. No, I want it to in a 3x2. Let's keep it like this, right? This is a 3x1. I want it in 3x2. Хорошо? So guys, tell me, for this point, how will I split first how will I split this area of interest, right? So basically, we will split on this axis or the vertical axis on 2. So here we have 1, 2, 3, 4, 5, 6, 7. Yes, we have 7. So basically 7 divided by what we want, which is 3, which is 2. That should give us 3.5, right? Sorry. For 3.5, we can't split inside this pixel and say that this pixel belongs to this area and this area. What we will do, we will just, for the first ones, split on just 3, and the others will be split on 4, right? So basically, this is the, let me try a different color maybe. Bigger. There you go. So basically, this is the first split. The second split, or the horizontal split, we will be splitting 1, 2, 3, 4, 5, 6, 7 divided by 3, right? So 7 divided by 3 is 2 point something, I think. Yes, so it's 2.333. So basically the first one will be just 2. The second one will be just 2. And the third one will contain 3. And there you go. Now, what you will have to do is, so for example, here we had 4, 5, and 6, right? Here we had 1 or 3, 2, minus 1. Can somebody tell me what should be in this area?
6.
Nice. Let's say, for example, in this place, we had 7, 1, 8, 9, minus 1, 2, 3, and 4. So this place would be
9.
perfect. In this area, no, we have 1, 3, 4, and 5. 3, 2, 5, and 6. Minus 1, 2, 0, and 0. This point will be
6.
6. Exactly. So do you guys now understand how ROI pooling is done? So basically it's just max pooling, but instead of having a fixed kernel size, we are now guessing the areas based on the expected output. So basically, doesn't matter the shape of the input that you give it, it will always give you the same output size. And this is why it's useful. This is why, where do we apply this concept? Yes, so we apply this concept here. So basically, doesn't matter what shape the region proposal algorithm gave us, the feature map, the corresponding feature map will always be ROI pooled into the same size and hence can be used with fully connected layers, right? So the important part is to use it with fully connected layers because fully connected layers give you require a fixed input size. So that's why we use ROI pooling before sending to fully connected layers so that we can convert the shape of any feature map that we have into the shape that we expect.
You want to say that region of interest pooling gives us like the location of objects of interest, yeah?
No. It doesn't really work on anything. It doesn't give you anything. So basically, it takes a feature map of a different size, of a very big size, and reduces its size to something that we expect. So basically, here we didn't say where the object is located. We didn't say maybe the object is here or the object is here. Only thing we said was we will take this region and summarize it into 1 pixel. So it's just max pooling, right? So the same thing, what max pooling does is
like
just
convert image to fixed size image, not
Exactly.
even image, but feature map.
Yes, so basically we convert
And
any feature
why
map.
do we need it?
Exactly, so that's what I said. After ROI pooling, we will be putting it through a fully connected neural network. Fully connected neural network, right? And fully connected neural networks expect a input size to be the same.
I got it, thank you.
You're welcome. So basically, fully connected neural networks require a feature vector. For example, this is 32. Once it is trained on 32, it cannot be trained on, inferenced on something, for example, 34 or 35. It requires all the input to be 32. That's why we use ROI pooling in this case. Is ROI pooling a bit clear now?
Are we doing max pooling every time? Or average pooling maybe, or other kind of pooling?
So for the
it's
definition
max
that we
pooling.
have here, it's max pooling. If, for example, in your case, you find that average pooling is better, nobody's ever going to tell you don't use it. It's still something that you can choose. So basically, if you write a research paper that says average pooling is better for ROI pooling than max pooling, then that's a good paper and we can publish it if it's not done already. So
Got it,
basically,
thank
it's
you.
not a constraint to use only maximum. Хорошо?
Yes, thank you.
We split it, start calculations.
Okay, I want to do it in the case if we like ROI pooling always like the shrinks the size of original image, like to the
Yes.
lower one. And what to do in situation if our region is too small, we need to upscale it.
We need to upscale it. Nice. Let's speak about this. It's going to be a very simple algorithm or very simple case. Draw. There it is. Ah, you can draw this. What is this? I know. It's nothing. I thought it would give you a matrix. There you go. So this is the matrix of interest. And it contains one value, right? Let's say just one value. Our ROI pooling layer should give us 2 by 2. What would you do in this case? You as a person who just wants the following, what would you do?
Just copy and paste free in all sections.
Exactly. Now let's take another example where we have 2 by 2 versus, no, make it black. Let's undo. And we want something which is 3 by 3. There you go. Let me put the values first and then you tell. So here we find 3, 4, 1, and 2. What would you do? Go ahead. All the answers are correct, actually. There's no wrong answer, to be honest. Okay, maybe it will be easier if we make it 4 by 4 here. Right? Okay. Yes, in this place, what do we put? I think
It
something.
will be 4 in all sections.
4.
Ta-da! There you go. So this is an edge case where it's very possible that the size of the input is smaller than the expected size. And what we can do, we can just upsample it and perform this task, right?
Okay, what about the case if we have 3 by 3?
Well,
Like
then
what-
all the answers are correct. So for example, if you put 3 here and then 4, 4, 2, 1, for example, or you decide to put 3 only here and then 4, 4, 4, 2, 2, and 1, 2. So it doesn't really matter. All the answers are correct in this case.
Okay, thank you.
Yeah. So it depends on what algorithm would be using. It doesn't really matter. This is like the edge cases that don't really change much in the calculation. Doesn't matter what you say. It's always going to be a correct answer. All the answers are correct in this case. Do you guys have any other questions about RCNNs, region proposal networks, RPNs? And region. хорошо. Do you guys have any other questions? Or should we finish the lecture? So I don't see any questions coming so far. Let's continue the lecture. So the next part of the lecture will be just on speaking about what Detectron is, what YOLO is, what are the differences, and just speaking about the architecture of YOLO. Nice. So we have Detectron here. Detectron is not really an architecture. It's not a family of architectures. It's not a new idea or something like that. It's just a library from Facebook that implements a variety of computer vision models. So it's not something that is like an architecture, new architecture, or a new research paper or something like that. No, it's just a library. It's just code for you guys to quickly be able to use any of these applications with the least amount of code possible. The good thing about it is it's fully written in PyTorch. It's very fast in calculations, and it provides a huge, vast amount of pre-trained models on a variety of tasks, such as object detection, as we are doing here, such as object segmentation, which we are doing here, or here also, we are doing object segmentation, DensePose, which is an algorithm that understands the dense or the depth of the human beings inside the image. The panoptic segmentation, it's kind of like image segmentation, but in this case, every single pixel must be segmented in one way or another. So we can see here that this pixel is, for example, sky. This is green or trees. This is road. This is a person one, person two. This is panoptic segmentation. Or, for example, landmark detection, such as what we're seeing here with the human beings. All of these models exist in Detectron. And the only thing you will have to do to use them, at least, is just change the name of the model that you want and the, of course, the processing that will happen after. YOLO, on the other hand, again, yes, just one single thing about Detectron. Detectron mainly uses RCNN family. So basically, Detectron uses the mask RCNN architecture and the faster RCNN architecture. The small difference between what mask RCNN and faster RCNN is, they're basically the same models, but at the end, instead of only predicting the class of the object and the bounding boxes of the object, we try to predict the mask. So what is this mask? It's just a, let's call it, do you remember autoencoders, right? So autoencoders, the output of an autoencoder, it's an image. We will have the same kind of functionality in this area, where the output of our model will be an image, and each pixel is either in the object or not in the object. So basically, it's a binary map or binary image that's called the mask, and it tells you where exactly in this bounding box is our object located. So just to see it in action, here it is. So this is the bounding box, and if you can see that there is some green surrounding the balloon, right? So this is the mask of the object, and this is what
actually balloon like started me with orange actually, but in the original it was red. Actually, like by this we like highlighted where balloon is.
Exactly, that's a great remark. So basically, you see that the balloon in this case is actually red, but we highlighted it using the green of the mask, right? So basically, this is the mask that is proposed by mask RCNN architecture, and that's what Detectron is using. YOLO, on the other hand, decided to create its own family of models. So basically, RCNNs separate the object detection task on two separate tasks. The first one is you find the regions, and then you simply classify those regions and just correct or fine-tune the coordinates of these regions. And if you're going for mask RCNN, you're going to be detecting the mask of these, what are they called? Of these objects, right? Inside the region of interest. Now, the second architecture, or the second family of architectures, is called YOLO. And YOLO, the name actually stands for you only look once. And the idea is that we will be doing all of the calculations, all of the image object classification and bounding box regression in the same feed or in the same forward pass. And for now, I would like you guys to ignore this part of YOLO. We will speak about it, so it's just a duplication. The important part to understand is the following, right? So here we see that we take the image, we send it through the neural network of convolutional layers. Usually in this section, the size of the feature maps continues to get smaller and smaller, right? And then what we will be doing, we will take this feature map and send it through a YOLO detector. So to understand what YOLO detector is, we should come here. So basically, at each one of these scales or each one of these detectors, we will be splitting the image into regions. So for example, the image of the dog will be, of course, shredded, like downsampled while it's going through the CNN. So the size will be getting smaller and smaller until we arrive to this kind of size, which we have 13 by 13, right? In this area, the images or the objects that we should be able to find are the bigger objects. So the objects that will occupy a big amount of space in the image. So basically, even if we shrink them to just a 13 by 13 segments, they will still be present there in the image and we can still detect them. And what we will put at each step of this grid, we will put the following classifiers. So basically, we will put 3 types of boxes, or you can think of them as anchors, right? So we'll be putting these anchors in here that will be predicting the following values. The coordinates of the box, so basically the X and Y of the center, the width and the height of the object, the object scoreness, so basically objectness score, so basically does the object exist in this area or not? And we will have in this case, for example, the class probability scores, right? So here we have the first class, second class, third class, fourth class, fifth class. So this is the output of normal classifier. Remember yesterday when we were doing the configuring of the YOLO v4 CFG file, we said that after we specify the number of classes inside the YOLO layers, the previous convolutional layer should be changed in the following manner. So basically the number of filters, sorry, I will do one simple thing, just so that they don't receive any messages. 1 second, guys. Okay. Now we're back. So basically, remember when we were configuring the YOLO v4, or you will be configuring YOLO v3 or any other version of YOLO, always inside the YOLO layer, you're going to be changing the filters value to classes plus 5 times 3 in only the convolutional layer that is previous to the YOLO layer, right? And this comes from the following reason. So basically, we want, this is the feature map, right? So what we want in the feature map to have space for the class scores, which is the number of classes, one value for whether the object exists or not, and the 4 coordinates of the box or of this object, right? And then we multiply that by 3 because this is the parameter that YOLO v3 decided to take. So basically at each point, we can predict 3 different bounding boxes. Just to, of course, we still have a lot of details to go through, and we will go through these details a bit later on in the lab. And hopefully also in the next lecture, we will be speaking about, what is it called? Yeah, the next lecture will be about image segmentation, as I remember, and object tracking. And the next one would be on GANs and facial regression, facial classification, facial recognition. So just to get a quick summary of everything we have said today, we've spoken about object detection. How is it different from classification? We spoke about intersection over union and non-maximum suppression. We spoke about RCNN and fast RCNN, faster RCNN, the mask RCNN architecture. And we've seen that Detectron is an algorithm that, or is a set of, is a library that implements all the different implementations or all the different fast RCNN and RCNN family in PyTorch. And we saw the YOLO VX family, which usually follows the same architecture as in here. So basically we perform classification at different scales. The first scale tries to find the objects in the smaller of the bigger size. The second scale tries to find the objects in the bigger size, the medium size, and then the last one is for the smallest size objects to be able to still find them. This is usually done by upsampling the feature maps of this stage and combining them using a residual block and concatenations. So basically we'll be combining them using concatenation with the upsampled feature maps from here and sending it forward and forward. If you guys have already studied, for example, an architecture such as UNet, you will find that this behavior is very common in such models. And we will speak about UNet and other models such like this in the next lecture. You guys have any questions so far or not?
No.
Anyone else want to share something else with you guys here? Now, the last part of the lecture would be to speak about mean average precision and understand what it is. For this one, there are questions? Okay, nice. Yes, you are also, if you would like to just go at home and then watch the video again and just stay with yourselves and understand again the lecture and then ask questions in the next session. I think the idea of doing a revision before the quiz can be very useful for you guys to just help you get better quiz grades, right? So basically on the next lecture, before we do the quiz, we will do a small revision of the concepts that we have covered during the lecture. And usually in that revision, I will be answering most of the questions of the quiz. So just pay attention to what I'm saying and it should be very quick, right?
Okay, thank you. It's a really great idea.
Nice. So basically, I just don't want you guys to have anyone have any bad grades. Again, it's not about the grade. It's just a. Where is it? Here it is. No, this is not it. Nope. There it is. So basically, I found this very cool tutorial, and it's step by step helping you to understand what mean average precision is for object detection models. And it's very simplistic. So basically, it just gives you a small example and then walks you through the calculations. If other people like the concept of, let me add this here. I found another tutorial also, which could be useful. Here it is. So basically, this one is unlike the other one. So this one is something that you would be more visual with and more explanations. This one is a small example, very simple example, but with manual calculations. I would like to go through this simple example first and then go through the other one later on to maybe enhance the understanding of mean average precision. Just from the name, so you can see that mean average precision score is, so basically the precision. We will take the average of some precisions and we will take the mean of this AP. So before going to understand what MAP is, we will start by understanding what precision is. And then we will go to understand what is AP or average precision, and then understand how do we calculate different APs to get the mean average precision, right? Let's start by the small example. So first we have this true class. So for example, we have here, it's positive, negative, negative, positive, positive. So basically this is the class of the object that we're trying to detect. So it's binary classification. This was the prediction scores of the model, and this was the predictions of the model, right? So how do we make the predictions? Sorry, basically using a threshold of 0.5. If it's bigger than the threshold, then it's positive, smaller, then it's negative. So these are the predictions of our network. So in here, we can see the confusion matrix between the between the predicted scores or predicted values, so y pred and y true. We see that 4 were correctly classified as positives, 4 were correct, 3 were correctly classified as negatives. I think this one is false positives and this one is false negatives. The precision score in this case is the following. So it's 4 divided by 4 plus 1. And the recall is 4 divided by 4 plus 2. Just a small question. Do you guys already know what is confusion matrix? What is accuracy? What is precision? What is recall?
Yes.
Is there somebody who doesn't?
Can you go through them quickly, like in brief?
Хорошо. This is very important. So basically here, this is the confusion matrix that we have just seen before. This is ground truth axis, and this is the predicted wise axis, right? This is for the positive class, negative class, negative class. So here the ground truth is positive and the predicted is positive. So these are called the true positives. And here we have the ground truth is a negative class. So for example, this is cat and this is dog. So this is the negative class, but the prediction was positive. So basically, false positive means it was falsely predicted as a negative value. Okay?
Vice versa.
Sorry. So basically, it was falsely predicted as a positive value, right? So this is what false positive is. Try to read it in this manner. So the prediction is false and the prediction is positive. So this is what false positive is. Just to remember how not to confuse between false negatives and false positives. In this rectangle or this index, we will have negatively predicted samples, which are in fact in the negative area. So basically, this is true negatives. This is good classification. And in this place, it's false negative or falsely predicted as a negative. So basically, the model predicted it as a negative, but in fact, it's not. So this is the area where we are intersecting between ground truth positive and predicted negative. So this is what false negatives are. Let's start with accuracy. Can somebody tell me what is the accuracy of this one? Accuracy is the simplest.
Positive plus negative divided by over values.
Amazing results. So basically 3 plus 1 divided by all the values here. So divided by 4 and 5, 6, 7. So it's 4 divided by 7, right? So this is the accuracy.
Yes.
I don't know what that is. Now let's go to the precision and recall. I think there should be some good diagram here. Here's the accuracy. As we said, true positive plus true negative divided by everything. Now the precision. True positives divided by true positives plus false positives. What does this mean? What can we interpret this as, right? So basically it's every time that the model say this is a positive sample, how many of these times, no, okay, let's go back. How many true positives or how many correctly predicted positives in the range or in the samples that the model has predicted positive? Okay, so basically true positives are the values that the model has predicted as positive, and they are in fact positive. False positives are the model of the values which are in fact which are not positive, but were predicted as positive. So basically, every time the model says this sample is positive, how much should we trust it, right? So if I say that this, if I just go around and say that this is a dog, this is a dog, this is a dog, this is a dog, how much can you trust my this is a dog classification? This is what we can say the precision. So basically, if he says this is a dog, how precise is this example, or how precise is this prediction? So again, precision is true positives divided by all or the number of values that are predicted positive. Again, we come back here just a little bit. Here, you see? So true positives and false positives are the ones that were predicted positive. So we're using this raw of predictions divided by this value, which is the positively predicted, the positively predicted and positively ground truth is divided by this raw, right? So usually it's between 0 and 1, of course, because we're dividing on something that is bigger or equal to it. Now, this is what precision is. So precision is how much can you trust a positive prediction. Another one would be recall. Let's go back. For recall is out of all the really positive samples, how many will the model be able to detect? So basically, we have all the values that are in fact positive. So false negatives are the ones who are really positive, but they were predicted as negative. True positives, they are truly positive and they were predicted as positive, you see? So out of all the samples that are positive, how many or what percentage is in fact predicted or is in fact classified correctly? So this one tells you the recall. The recall, you can think of it as just how much is your model able to find this specific class. So for example, if I have 10 dogs and the model was able to identify 6 of these dogs, then basically we will say 6 divided by 10. So basically it's 0.6 recall, right? So these are the different metrics that we have. Let's go back here. So accuracy is the true positives and true negatives divided by everything. Precision is true positives divided by the ones that are predicted as positives. And recall is true positives divided by this row or the ones that are in fact positive. F1 score is like a mean between precision and recall. So we can see it here. It didn't speak about it here, but basically F1 score is just a sort of balance between precision and recall. Now that we have this covered, let's go back to our metrics and understand something called as the precision recall curve. Are you guys familiar with precision recall curve? Let me just put the chat here. Okay, nothing really pushes. Okay, so the precision recall curve is the following. One would ask me, so there was something that I really struggled with to understand this thingy. What is the thing that's moving in this case, right? So usually, if you have an x by y, you just move the x and you plot the y, right? In this case, it's not the case in here. So basically, we're not moving the recall and finding what the precision is. We're moving something else. We're moving a certain threshold and seeing what are the corresponding values for precision and recall. The thing is, when you move this threshold that we will be speaking about, it will be the same thing as kind of moving the recall, but we are not moving the recall. So this graph is a bit misleading for me, or at least if you don't see it, if you don't understand how it is made, you will always suffer to understanding it. Recall is not being moved around and seeing what is the precision of the model. What we are truly doing is we are going through different thresholds. So basically we take threshold and say, if the model predicted this, so 0.7 here. In the first time, we said that 0.5 is the threshold. We would say if it's 0.3, then it's a negative class. If it's 0.7, it's a positive class. Now what we will be doing is kind of the same thing, but again and again. So we will be changing the threshold and calculating the recall and precision at each one of these thresholds. So basically, we say that the threshold is 0.2, meaning if a class is predicted with 0.1, it's a negative class or sample. And if it's predicted with 0.3, then it's a positive sample. And then we go to the next step, which is 0.25, for example, and then the threshold becomes 0.3, 0.35, 0.4, 0.545, 0.6. And at each one of these thresholds, we calculate the ROs, we calculate the recall and the precision, and we put a point in this graph. So basically, we put a point here, then we put a point in here, then we put a point in here, 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 and there you go, you find your graph, and then you just connect the dots. Do you guys understand so far what is the precision recall curve?
Nope.
Nope.
May I try to give you an example of this?
Yes.
By this call. Actually, like at the very beginning, it's very like top left. We have a model which do not like classify find all the ones in our data set. But if the model says this is a one, the model says with high confidence. But we are not satisfied with it, and then we try to change our threshold. And actually, model starts to find the more and more ones, because the model wants to label the one everything what the model see, and but by this we increase the number of mistakes, like misclassified for like zeros, and this precision is going to down. But in the end, it will like the bottom right. The model like actually finds all the ones what we have in the data set, but actually also like has a lot of false positives.
That's a very good explanation. So basically, in the extreme cases, when we have the threshold set to the maximum value, meaning that the model will not be classifying many samples as correct, right? We'll not be classifying lots of positive samples, right? So whenever the model says that this is positive, it's always going to be correct. So it's 0 to 1. I see Maxime is doing something that's good. So we're moving the threshold from 0 to 1. And in these different steps of the threshold, basically we just calculate, make the new predictions first, and then calculate the recall and precision at that step. We put it into this plot, and then we see how the, what are they called? And we see how the plot looks like. We will, just a small question I would like to ask you guys. Which one goes up when we increase the threshold, and which one goes down when we increase the threshold?
One of them will go up, and the other will go down.
Exactly. So this is why they kind of look like they are like there is some relationship between them. So basically, when we move the threshold going up, one of them will go up and the other one will go down. Now I want you guys to tell me which one goes up and which one goes down.
I think if we increase the threshold, the precision will go up.
The precision would go up if we increase the threshold.
Yeah.
Okay, tell me what that means. How did you find this out?
My answer should be I guessed, but I think it's we are increasing When we increase the threshold, we're increasing the result to be, we're going toward positive results, I guess.
Exactly. So basically, precision, what precision means, when the model says it's positive, how much time is it correctly positive, right? So basically, if we reduce the amount of times the model says it's positive, so you can think of it as when we increase the threshold, the amount of false positives decreases, right? More weights to positive results. Yes. So basically, when we increase the threshold, we will start removing some of the false positives, right? Meaning, let's imagine that true positives are the same, right? And imagine that the threshold only influences the false positives, right? So let's imagine this scenario. This is the line, right? And here we have some samples. Let's make it red. Yep, this is falsely, this is false. This is also false. Negative sample, negative sample, negative sample, negative sample. Here we have a positive sample. Positive sample, positive sample, positive sample. Let's say it's like this. Now let me use this. And yes. So when we increase, when we had the small threshold before in this area, right? This means we had some false positives in this case, right? So how many false positives do we have here? 2. This was the threshold.
Yes.
So let's say 4, sorry. So basically in this model, we have 4 divided by 4 plus 2. This is the precision.
Yeah.
When we move the threshold a little bit, let's put another one. Let's make it this color. So when we increase the threshold, this is what happens.
More precision.
How many false positives, true positives do we have? 4. How many false negatives do we have? False positives, I mean?
No, 0.
0. So when the threshold was small, our precision was small. When the threshold was high, our precision was high. So this, let's think of it as the following. Let's write it like this. This is a graph that says, there you go, threshold. This is, sorry, threshold, precision. As the threshold goes up, the precision also goes up. Now let's understand the same example and see what happens to recall. Exactly, yes, this is, of course, we said this before that one would go up and one would go down. So let's see how does the recall go down, right? I will just go down a little bit to the recall formula. Here's the recall formula, right? Annotate, eraser, right? For the first one, can you guys tell me what is the value of true positives?
Is the same, it's 4.
It's 4 divided by. This is a bad example. Huh? Okay, wait.
Because Imad, I need to say what your assumption was not correct about the precision, because actually the threshold affects and false positives and true positives, because some of the true positives may be here.
Exactly, yes. So basically I will add another false positive here. Like this. I will add another one here, just to understand.
Yes, yes, this is like more accurate. Yes.
Okay, now let's do the calculations again. Let's say our threshold was here, the first threshold. The second threshold we will put here. Let's calculate precision, let's calculate the recall. For the first example, recall is true positives, 1, 2, 3, 4, divided by true positives and false negatives. So 4 plus, what is the false negatives?
5, not 6.
The last red one is false
Plus
negative.
1.
What are the false negatives? Can somebody tell me what are the
The
false?
true results which was classified as negative.
Yeah.
So it's a positive result classified as negative.
Mhm.
This is the threshold. Where is the positive result that is classified as negative?
At the left.
This one.
Yes.
So 4 plus 1. What is 4 divided by 4 plus 1?
0.8.
Хорошо. Now let's calculate for the second threshold. True positives in the second threshold. How much? Go ahead, tell me
That's
that.
two,
Especially
two.
the people who don't understand yet. Please tell me. If you don't understand it, this is your time to tell me. Go ahead. How many true positives for this threshold?
2.
2 divided by, again, 2 plus how many false negatives do we have?
Three.
False negative, it means falsely
Three.
predicted as a negative. So something which is positive, in fact, but we predicted it as negative. So we are looking at this area. How many positive samples are in this area? Can somebody tell me?
Seems it's 3.
3. So recall became 0.4, and here it was 0.8, right? So basically what happens is, while we are changing, let me add another dimension here. Yeah. Sorry. This is the recall, right?
Now we know not only bias variance trade-off, but recall precision trade-off.
You see? Let's change the color here just so you guys can understand. So there you go. So while the threshold is going up, our recall will be going up. Oh, no. No, sorry. This is this color. Let's undo. Yep, like this. This is like this, right? So while the threshold is going up, the precision is going up. While the threshold is going up, the recall is going down. Хорошо? We saw how does this influence, how does the threshold influence the different recall and the precision values. Does anyone have any questions about recall and precision so far?
No, the
I
explanation was
have a
clear.
question about how you can compare efficiency of different model by using this curve precision.
We'll speak about it later.
recall.
We'll speak about it later.
Okay,
We'll speak about this
okay.
later. Yes. So for now, we understand how do we build this curve. Simply, we change the values of the threshold and put point. So basically, this is the point for precision and recall at certain thing. This is a point for another one. This is a point for another one. This is a point for another one. So basically, we change the threshold, calculate precision and recall again, and put this point again and again and again until we have such curve. After we have the curve, so we have here the formula for F1 score. So F1 score is just a sort of harmonic mean between precision and recall. So it's just basically, how do I say it? It's a balance between precision and recall, right? So basically, it's one number that describes both of them. Average precision, you can think of it as simply the average of the different precisions, right? So here you made different thresholds, at these thresholds, you had, let me annotate. So for example, you calculated at threshold 0.25 and had your precision as 0.14. And then we say as we increase, the precision increases. So basically 0.20, 0.42. And then at another step, it was 0.6, 0.8, 0.9. So AP, the one that we are talking about, is only an average of the different precisions that you had while moving your threshold. Simple, right? The average precision is just the average of the precisions you had while moving your threshold. Now, it's not an average directly. So usually, as you have seen it with everything that we do, instead of just using the average, we use a weighted average, right? So basically, if we ignore this formula for now, so basically what we are doing is we're taking the average of the precisions at different thresholds by just weighting these precisions using a certain weight. That's it, right? So it's basically the precision with a certain weight. Now the weight in this case is just a small formula here. So it's basically the increase in recall between the different steps. So basically, let's say we had recalls, recall decreases. How much? 4. What we do is we weigh, this is the recalls, the precisions equal, let's put an example here. So 0.1, 0.3, 0.5. Let me just find who is speaking. Nice. As you see, so IP, or average precision, is just a weighted mean of these precisions at different thresholds using the weights of and the weights are extracted from the recalls. How do we extract them? Using the following formula. So basically, recall at step, precision at step 0 is 0.1. The recall at the previous step in here is 0. No, wait. Recalls at n. But there's something here that I'm not getting.
The last recall, according to this formula, is equal to 0.
Yes, but the thing is, the rest. Yeah, makes sense. Oh, sorry, makes sense. So yes, so basically 0.1, right, is weighted using the following. 0.8 minus 0.9. So this is the weight of the first precision plus the second precision and its weight. The second precision is 0.3 multiplied by its weight, which is 0.7 minus 0.8. And we continue doing this thingy, this operation, and again and again and again until we finish.
Seems we are going to get negative number.
Shimo.
Because we are multiplying negative by negative number.
Ah, sorry. It's 0.8. It's 0.9 minus 0.8. You're correct.
Yeah, much better. And
yes, sorry. 0.7, sorry, minus 0.8. Thanks for pointing this out. There we go. So 0.1 times 0.1 plus 0.3 times 0.1 in this case again, and again and again and again until we arrive to our average precision. So this is what average precision is. Average precision is only, what is meant by recall here? Don't we have only one recall for a model? That's a good question, but remember, we have different recalls at every threshold, right? So we move the threshold from 0.2 and then calculate the recall and precision at that step. Then we send the threshold to 0.1, calculate the precision and recall at that step, send the threshold to 0.5, calculate the precision and recalls. So basically we have different steps, and at each step we have different recalls and precisions.
Imad, can you please repeat the calculations one more time? Because
Yes.
I lost the idea.
Again, the formula is very simple. Ignore this part so far. Average precision is only a weighted mean of the precisions, right? So basically we will be doing weighted mean of the different precision values at different thresholds, correct?
Mm-hmm.
You understand how did we get different precisions?
Yes, by moving from 0.2 to our several thresholds, several precisions. Okay.
Хорошо. Now, the weights of each precision value is given by this formula. Is given by this formula. So it's recall at this step minus the recall at the next threshold. So here, let's do the calculations. These are our different recalls, right? The first one was 0.9. So basically it's 0.1 precision. There it is. Multiplied by 0.9, which is the recall at step 1, minus 0.8, which is the next recall. Plus, this is the first step of the precision. The next step of the precision would be 0.3 times tatati patata. Did you get it?
Why we have 0.9 minus 0.8 at the first, and then 0.7 minus 0.8, I don't understand.
No, sorry. I corrected it and made the same mistake here. Yes, thanks for pointing this out. Yes, let me erase and write it again. Yeah, that was just a mistake. So 0.3 times 0.9 minus 0.8 plus
0.1.
Thank you.
Mm-hmm.
0.3 times 0.8 minus 0.7. You are correct. So this is how it's done, right?
Mm-hmm.
Did you guys get it?
Yes.
So again, what is average precision? It's just the weighted sum of precisions, right? So it's very direct. Now,
what is the purpose of it?
What did you say?
What is the purpose of this average precision? Why don't
What is the purpose of this one? So it's basically another way to summarize your precision recall curve. So with one number, you can understand the precision recall curve. You can summarize the precision recall curve with one number. Another good number to summarize the precision recall curve is area under the curve, AUC, right?
Yes.
You guys know what AUC is?
Yes, it's good.
Nice. So area under the curve summarizes the information that is present in the curve in just one value. Average precision summarizes again the precision recall curve into a single value that represents the average precisions using the weighted by this formula of the increase in recall. The AP is a weighted sum of precisions at each threshold where the weight is the increase in recall. So if we get a high AP and a high increase in recall, that's a good one. Low increase in AP and low AP and a low precision and low increase in recall, then that's a bad one, right? So this is what AP is, average precision. Do you understand what average precision is?
Yes.
Nice. Now let's go to what mean average precision is. So definitely you might have guessed that we will have multiple average precisions. One good reason would be because we have different classes, right? So if you have different classes, you will have an average precision for each class. Because precision and recall are binary, right? So they only work in binary classification, positive and negative. If you have different classes, then for each one of these classes, you will be calculating precision and recall. You understand that?
Yes.
Nice. So that's one way of getting different average precisions. And then, well, later on, we will just take the mean of these average precisions and give you the MAP, mean average precision. For now, let's speak about intersection over union. I think you guys already understand what intersection over union is, but let's check it here. So basically, how do we convert bounding boxes into what we are talking about here as correctly predicted or not correctly predicted? And we do that using intersection over union. So if a model has a very high, if a bounding box or predicted bounding box has a very high overlap with the ground truth bounding box and their IOU is high, that means that prediction is correct, right? So here we have, now that yes, so these are just examples of different values of IOU. So in this case, IOU equals 0.2. You see, this is the overlap, and this is the union. It's not very good. In this case, it's 0.5, and this one is a perfect one with 0.9. It could be more perfect, but it's very good already. Nice. Now, how do we get from a class IOU into positive and negative? So previously, we saw how do we go from having positive and negative, right, like this, into calculating precision and recall. Now, before going into precision and recall, we will just calculate this. This bounding box was correct. This bounding box was not correct, right? And in this case, we will do the following formula. Class of our depends on the IOU. If it's positive if the IOU is bigger than a certain threshold, and it's negative if the IOU is smaller than a certain threshold. So basically, if I say there is a cat in this image, and my bounding box is is inside this image, then this is a correct classification, right? So basically, this is positive sample with correct classification. If I say, for example, there is a cat in here and there was no cat in there, so basically this is a false positive, right? If I say there is no cat in this area, so basically this is a false negative. And if I say there is a dog in this area, also again, it's a false negative. So this is basically how do I go from IOUs into just having positive and negative classes and calculating the average precisions on these. The mean average precision, there you go. So these are the different, so basically what we will be doing, as we just said before, we will take the average, we will take the intersection over the unions, and using those, we will be calculating or we'll be plotting the precision recall curve. From the precision recall curve for each class, we'll be calculating the different, what are they called? Help me out. We'll be calculating the different average precisions. Yeah, there we go. So here we have, for example, two classes, let's say cats and dogs. This was the average precision of dogs. This was the average precision of dogs. And we just take the mean of the average precisions of every class and we get the following. Do you guys now understand the whole story behind mean average precision? So basically we take intersection over the union of different bounding boxes. We try to find which ones were correctly classified, which ones were not correctly classified. So basically we calculate false positives, false negatives, and true negatives for every class. And then for that class, we go ahead and calculate the average precision. And then we just take the mean of all the average precisions of all the different classes, right? Looking at your
Yes.
Does anybody have a question about what average precision is and what mean average precision is?
Actually, my prefer mean average precision because we skip it too fast.
Which one?
The mean average at the bottom of the article.
Okay, let's go back to it. Mean average precision are evaluated with different IOA thresholds, where each threshold may give different predictions from each. To calculate MAP, start by calculating AP of each class, and the mean of APs for all classes is the MAP. So basically, this is just the core that you guys would like to understand. First, remember the threshold for classification that we were using before. Now it is the threshold for an intersection over the union, right? We said if we want to convert bounding box predictions into just the previous values of positive, negative, positive, negative, positive, negative for every prediction, we should calculate the intersection over union of this box with the ground truth. If they are higher than a certain threshold, then we will calculate this one as a positive example. And if it's less than the threshold, we will calculate it as a negative example. I see that there was a question. Do all models have background class? Can you repeat the question just so I understand that I understood the idea?
I think he's saying, like, does the object detection models have a background class?
Yes and no. So basically, different algorithms count the background as a class, and others don't count it as a class at all. Is this your question?
Okay, one more time. Okay, why we have two numbers of AP in this case?
Because we have different classes. We don't have two numbers of AP. Let me show you an example of what APs look like. It's not just two numbers.
Is calculated for one class, and for different classes we calculate different average precision. And taking mean of all these different average precision, we get mean average precision.
Okay, in this case, an AP is based on using the different thresholds. Yes.
Yes.
And an object detection. What means threshold? In this case,
object detection, the intersection over a union.
Like it's big enough or not big enough. Yes.
Exactly. Yeah. This is what we said here, right? Here is the threshold. We call it positive if the intersection over union is bigger than the threshold. This is the threshold we will be playing around with to get different precisions and recalls. Then we take the mean precision, and then we take the AP average precision, and then we take the mean of average precisions of all the different classes. We will see how the outputs. Nice, thank you, Dimitri. So we will see the evaluation of object detection models with multi-classes look like. You will see that every class has its own average precision, and then we will have different. Then we will have the mean average precision. We also will have the F1 score, and we still will have the precisions and recalls. These are also very good metrics that you can use. Mean average precision, I don't really like it that much. Sometimes, I mean, I had a very good, like I had an example, not an example, I had a case where mean average precision was high, but the model was actually not doing a good job, and the mean average precision didn't detect it. So this is it for the lecture part of the course. Let's take a small break and go back to the lab.
I'm not sure that small break will okay because it's lunchtime.
How much time do you guys need? Yes, sure.
3 hours.
That's good. Let's make it just a 5 minutes break. Eat some snacks, right? And we come back, we finish the lab very quickly because the lab is actually the same thing as we did yesterday, right? So the lab is going to be just using, is still useful. And yeah, I wouldn't say SSD is useful. Yeah, just forget about single shot detector. Yep. It maybe someday somebody will make a newer version of SSD, but so far the best models are either faster RCNN based models or YOLO based models. And actually, I just heard, like, I was speaking with some of my colleagues at here, and they told me that there's a new model that's even better than fast RCNN, better than YOLO before, and faster and smaller. So I will check this new model. They checked it and they said it's very good. I will check this new model. If it's very good, I will actually present it in the next week.
Yes, it will be helpful.
Yeah. Okay, so guys, let's take a small break. Like, wash your faces, eat some snacks, and we come back for the lab part. The lab part is going to be very simple and very easy, so it will be very short, and you can guys go ahead and eat lunch right after.
How small?
Okay.
The break is supposed to be. Imad, how small we will have break?
5 minutes.
5 minutes. Okay.
5
See you
minutes.
in 5 minutes.
See you guys in 5 minutes. Hey guys,
We're still
we're
here.
back. Is everybody back?
Imad, can I ask
Yep.
a question?
Yeah, of course, go ahead.
What should we do if we want to find some specific to solve some specific problem? For example, we want to find excellent the bottom part of the detection rectangle. For example, for the tracking problem, when for pedestrian or for vehicle, we should excellently detect the bottom part of the detection rectangle. What metrics should we use to find that our neural network perfectly shows the bottom part of an object?
This is a great question. There is no such thing as a universal metric. So for example, accuracy, F1 score, all of these things are not universal. So these are just scores that you can, metrics that you should use if you don't have any domain knowledge. But in the case where you are building an application specific algorithm, you need to have an application specific metric. So basically you will be defining how your metric will look like manually. So either maybe you would change the weights of each sample, maybe basically the contribution of each sample, or basically you will go or specify some weights for the lower part of the what is it called? The box. So basically intersection over union does not mean that it's not calculated basically. For example, the intersection is not just one pixel, all the pixels have the same interest or have the same weight. Basically, you might change the intersection over union and keep the lower pixels of the object having more weight or more contribution to both the union and to the intersection. This way, you can change change the metric to your own need, as you just described. But again, it's very domain specific. So basically, if you have some domain knowledge about some metric that is very useful for this case, then go ahead and implement that metric. Do not use something that is general or generic.
Okay, thanks.
Thank you. Do you guys have any other questions? I see that there are none. I'll just close the window. Let's go. So for the lab part, I will try to do 2 labs. So basically, I just want to show you guys an example code. The first one would be the code for Detectron. How can we use Detectron models? And the second one would be YOLO v5 or YOLO v4. Yeah, YOLO v5 using PyTorch. Let me start directly by.
Can I ask a question?
Yeah, of course, go ahead.
In the lab yesterday, we predicted something or just found the bounding box of the YOLO model by writing the command that you gave us yesterday. In industry, do we use the same method all the time? If we deployed the model on something like a microprocessor, microcontroller, it will be the same, or
no? Inference in industry or in real life, you cannot really use this function directly. So it's not going to be like what is it called? So it's not going to be like a command where you say darknet detector, you give it the image and the other stuff. So it's not like that. This takes a lot of time. Basically, at each image, you're going to be loading the weights again and reading the configs and all of these things. You shouldn't be doing them again and again. So that's why there are things that are called as servers. So basically, there is runtime servers. One easy example would be a OpenCV, what is it called, based runtime. So basically you have a RESTful API, and the RESTful API will read the image in OpenCV and then send the image through a wrapper of the model. So basically you will use your model, load the weights of the model. So usually in these cases, Darknet does not really have something wrapper for PyTorch for Python directly. So in most cases, you might want to convert the Darknet weights into something else, such as ONNX or TensorRT. And using these TensorRT files or ONNX files, you can create easily, you can create a new, what is it called? Help me out. You can create a new model object inside Python, create a session in there, and then just run your images through that model and through that session, right? So this is one way to do things simply. There are other examples. So for example, you can do it in gRPC. Instead of just RESTful APIs, you can just do it with ONNX runtimes directly. There are runtimes that are provided by TensorRT directly also. So you basically just give it the runtime. You give the ONNX just the, I forgot, yeah, the TensorRT engine, for example, and you send it through the TensorRT runtime. So there are different ways of using the weights that you have right now, compiling them again sometimes, or well, converting them into different types of weights and then hosting them on the server. So there are different methods. Depends on mainly what is your input. So what is not your input. So what are your starting weights? So if you have darknet weights, or you have PyTorch weights, or you have TensorFlow weights, and then depends on where you will be putting the server. So basically, if you're going to be putting the server on edge devices, usually in these cases, then your OpenCV inference is going to be too much computations. So in these cases, you should go for ONNX runtimes. If you're going to be doing it on a, what is it called? On the cloud, in these cases, then you should just do whatever you want. Usually a Python runtime with just a RESTful API or gRPC API would be good enough for you. If you're going to be doing it on mobiles and this laptops and what is it called? The browser. In these cases, then there are like some TensorFlow, what is it called? Runtimes that you can easily use, and it's pretty quick. So these are just a small map of what you should do depending on where you are. Does that answer your question?
Yes, thank you. But I have another question. Is like, is there any like tutorials on how can I do this stuff, or like?
Sadly, this part, the inference part or the deployment part, is the least tutorialized. So yeah, you're gonna require to be either working in a team where you have a lot of DevOps engineers already with you and they know what's happening. And basically, you just integrate the team and you learn how they do deployment in your company. If you're going to be doing it alone, then just go ahead and use anything you want. So basically, really, if you're not in industry and you don't have like very strict client requirements, you shouldn't be worried about using ONNX or TensorRT and these hardware stuff.
Okay, thank you so much.
You're welcome. So quickly, let's now start speaking about the lab, right? I'm going to switch laptops now and come to this bad boy. Let me see if it's the correct screen. No, it's not the correct screen. Oh. Why does it keep on giving me this one? Let me stop everything, right? Yeah, you guys can see this Detectron.
Yes.
Nice.
Yes.
Nice. So basically, this is an introduction to the Detectron 2. Sadly, Detectron 2 already came with a very good beginner's tutorial for how to use Detectron on Colab, but now they stopped the support for this one. So sometimes it's not going to be efficient if you use the latest versions of PyTorch and the latest version of, what is it called? Of Detectron. So for now, let me just put my glasses on so my face doesn't hurt. And the first step is to install basically the install the what are they called, the dependencies of Detectron. And then here we will be downloading Detectron and pip installing it again. So it's just a PyTorch library, so pip installing works very well. One problem that you might always get on Kubeflow on Colab is that, yes, wait, let me open the video here.
We don't have any model, right? This lab.
You guys can see my face?
Yes, we can.
Yes, we can see your face and your screen.
On which screen? Yes, show.
You look different in both cameras.
Yeah, in the two different cameras. So basically, just there's a small problem because do you have this lab in Moodle? Not yet. Let me put it there. Yes, you are right. Or I will share it in Telegram first, and then I will share it in the Moodle, because usually Moodle it takes a lot of time.
Up to you.
Oh. This is in the channel, in the Telegram group, right? I sent it. Yeah, in most cases, you're going to have to restart the runtime because Colab already comes with some requirements already set up with different versions. And usually Detectron will require different versions. So there will be some conflict. Just restarting the runtime will solve all of these problems. Here we will be just importing some of the models, some of the modules of Detectron, and some of the things that will help us with visualization and stuff, right? So we downloaded a small image of a horse, people, and some fences and trees, right? And now let's check how do we build our Detectron model. Here we will see an example of using mask RCNN. So you can see here, what we will give it is only the YAML file in its library where mask RCNN is described. So basically in Model Zoo, we get the config file for this Model Zoo from their Model Zoo. And basically we create this config. In the config, you will usually have the threshold. So this is the IOU threshold, not the IOU threshold. This is the prediction threshold, sorry. So this is the prediction threshold for setting if the object exists or not. And yes, yeah, and this is just for the weights of the model, right? So this is the weights of the model, and these are the configs or the description of the layers of the model. We wrap this inside the default predictor. So this is just a class from PyTorch, from Detectron that simplifies basically the predictions, gives you better visualizations, gives you better formatting of the output. We will see the output. How does it look like right now? Just as you would expect, we send the image through the predictor and get our outputs. I will try to run everything. And yeah, we will speak about what's the content of this output later. The content is good. Bye. Oh, is this quick? Yes, it's quick. Nice, nice, nice. So let me interrupt. I shouldn't interrupt the execution because we're training here. Okay, so basically the output of the predictor will be a big dictionary that contains the following. So basically dictionary at instances will give you the output. The content of the output in here will be, I think it could be discussed in this area, right? So we will have the following prediction boxes. So these are the boxes with the coordinates of the objects. This is the score or the confidence score of the classification. The predicted class is a vector of 0 number of categories. Prediction mask. Now the mask is what we said. So basically it's, help me out. So it's like an image with binary values. The object is in this pixel or not, the object is in this pixel or not, the object is in this pixel or not. So these are what the prediction mask is. If you're going to be using some sort of a model that predicts the key points, then you will find them in here. And yeah, semantic segmentation, of course, these are for other types of models. What mostly we'll be working with is either object segmentation or object detection, and all of them you'll be finding them here. If you'll be looking for stuff related to semantic segmentation, you can find them here. And of course, panoptic segmentation, other these things. So this is the model output format for the default predictor. Now let's go back. Here is what the prediction classes look like. So for example, we found how many objects did we find in the image? 1, 2, 3, 4, 5. So we found a variety of objects, and the first object was class ID 17. The others were class ID 0. Class ID 0 is usually a person. So basically, these are people. 25, 25, and 25. This is another class, and 24 is another class. And we can here see that the tensor of the predictions or the bounding boxes uses a different format than the one we used in YOLO v4, right? Remember, YOLO v4, first of all, used values between 0 and 1, meaning the values are relative to the size and height and width of the image. And in this case, the values are absolute. So basically the values inside the image. Another thing is the output here. It follows, as I remember, let me check here. They're not saying. So as I remember, it's X, Y, width, and height also. We will find it in this area. Yes, so X, Y, X, Y. So basically it's, no. So basically it's this point with this point. So these are the, this is the format that this model uses. It's not the same format as the YOLO v4 uses, and it's not going to be the same format as YOLO v5 does. So every single version of every single model uses its different formats, right? Now, this is just the metadata catalog. This is the one which will be doing the conversion between index of the class and the name of the class. So this is the metadata catalog. So for example, here we don't see class ID 0, but we see class person 100%. And you see the results. So person, 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 person. This is a horse. This is umbrella, umbrella, umbrella. Backpack, right? I don't know, umbrella. Yeah. So basically, it's very good. So you see the results are pretty impressive, right? And these are the results of mask RCNN, which is just faster RCNN plus predicting the mask. Let me check the chat. Nice, there's nothing. How do we do the training on? Nice. So to do custom training on a new data set, we will do this the following. So basically, we will download the data set. Here's the downloaded data set. It's called Balloon data. It has training images and training. So basically, training images. Here they are. Are you still here? Yes. Here are the training images of the data set. Here are the validation images. Now let's look at where do we get the annotations. So the annotations in this case are inside a JSON file. Let's look for the JSON file. So it's called via region data. Where is it? It should be somewhere here.
It's in image directory.
An image, yeah, AMG directory. So it's inside the train and yes. So here it is. Sorry. Yeah, thank you. So there you go. So we have a format of the following. So this is another way of describing the boxes inside an image. So here is the image ID. The reference of the file is usually just useless. The size, which is the area of the image in pixels. File name, useless information, and then sadly it's not working anymore. There you go. So here we are not describing the bounding boxes, we're describing a polygon surrounding the object. So basically we're doing object segmentation, right? Let's come here. We're basically describing different points in this region that give you the person, right? So this is what polygon means, right?
So it's a mask.
It's not a mask. It's a different way of making the mask. So you can either make a mask or use polygons to build a mask. In most cases, going through each pixel and annotating it on and off takes a lot of time. That's why to annotate for annotations, we use this polygon methodology. So if you're going
But
to use,
everything inside this polygon is a mask.
yes, everything inside the polygon is what we consider as our mask. Yep. So here are the x points. These are the x coordinates of the points inside the mask, and then there is another one for all y. Sorry, all points y, and of course there is the class also. Let's remove this one. Now let's come back and see how the data is being read. Detectron also does not read images in JSON or data in JSON. He requires images to be read in his own format. And basically, we will be registering something called as data catalog. Let me just stop the register because I already did this. Nice. So basically, what we will be doing is we will be registering a new data catalog for every part of our data. So basically, for the training, for the testing, and for the validation, we will have a different dataset catalog. We register
like,
the data.
We are doing data loaders, yeah?
Yes, exactly. So this is the part where we will be doing the data loaders, right? So first we will give it a name so we can access it later on. And then with this function, so basically it's a Lambda function. And what we do is we will return a set of records or so this is, let's call it a list of records or list of dictionaries. The dictionary will contain the following. So every record is a dictionary that contains the following information. So file name, I have image ID, height and width of the image, and then we have this, yes, then we have a, for every object inside the image, we will put another, what is it called? Dictionary that contains the following information. The B box, which is minimum x coordinate, minimum y coordinate, maximum x coordinate, maximum y coordinate. So basically the two most left top point and the right bottom point, right? So this is the B box. We provide the B box mode that we will be using. So I think they can read B boxes in XY, 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 YA, WH, so basically the center point and the width and height. And they can, all of them have either absolute values or relative values regarding to the image height and width, right? And then the category ID. Usually the category ID, you will also be reading it from the JSON files. But since we are not using any different classes, we're using just one class. Here we have a category ID equals 0. And this is just for the segmentation part. So basically we send in this what is it called? The this polygon as an array of the different X points and Y points, right? So basically we will be creating, we'll be just creating a, what is it called? A array of different X, Y coordinates that come from the all points X, all points Y that we got from the JSON file. So you see, it's a lot of processing in this area. First, we read the JSON file, load it. Then for every image, we create a dictionary containing the file name, image ID, height, and width. Inside that dictionary, we create another dictionary for every object containing information about the B box, the mode, the segmentation, and the category ID. Yes, after we do this, we finish with the dataset catalog. We go to the metadata catalog, and the metadata catalog usually has the same name as the dataset catalog, but it only keeps in mind the classes, right? So basically the order of the classes, this is class 2, class 3, class 4. So basically using this one, you will be doing the mapping between the ID of the class and the name of the class. We can check some of the images that and verify that everything was read correctly using this function. There we go. You see, these are the polygons that we have described earlier, and this is the bounding box. So everything here looks very well. The visualizer is only here to help you guys with visualization purposes. So basically, you take the image and you give it the metadata and basically just the dictionary that you'll be getting. And it will be drawing all the objects inside the image based on the metadata that you just created. So just for the class names. The training. Again, remember, for just running inference, we created simple configs. We gave it where are the model configurations, where are the weights of the model, and the threshold, and then we created a predictor on that one. For training, we will do something very similar. So basically, we will get the default configurations. We will give it the name of the training dataset catalog, right? Remember this one, the dataset catalog. We will give it the name of the training dataset catalog. We will give it the name of the testing dataset catalog if we have. We will give it the configs of the model. We will give it the weights of the pre-trained model. The number of workers is just to help you guys train load the images faster. Images per batch, also useless. This is the base learning rate. You should change this a little bit. Usually this one works very well for me, but you can change it a little bit. Max iterations usually is here, it's very small, just so we can get the lab quickly done. But this is the number of epochs that you guys have seen before. It's the same thing as max batches for YOLO v4. Remember that? So here it is. So solver, you set the number of epochs that you would like to train for. Yeah, and that's it. Yeah, the number of classes. This is very important also to change. If you guys would like to have, for example, multi-class classification, then usually just come here and say 6 or 5 or something like that, right? From this, you will go ahead, create a default trainer instead of a default predictor. So basically, we'll be creating something called a default trainer. Resume or load. So basically, we're saying resume false. Basically, if you train some model and train again, continue the training again, do you want to start from scratch or to resume? Basically, in here, in this the purpose of this lab, we will be restarting from scratch every time I do the training, just so that we have something that is reproducible. And there you go. We have the architecture first of our beautiful Mask RCNN. So basically, we have a backbone. Remember the backbone? So it's a feature pyramid network in this case, instead of using a VGG, basically. Yeah, followed by lots of bottlenecks and DresNets, and all I see here is just convolutional neural networks, some batch normalizations, convolutional neural networks, region proposal network. Remember, so this one is the backbone, which in our yes, I'm still here. Yes, so remember in the lecture part, we described the backbone as just VGG. In here, they improved VGG by using something else called feature pyramid networks. We will speak about feature pyramid networks in the next lecture, but they're just a cool way of extracting cool or much more informative feature maps, right? After the feature pyramid network backbone, we have the RPN, which is the region proposal network, right? And again, the architecture is just convnets and some ROI poolings, right? Flattening, then some linear models, you see? Output features here, not box predictor. You see the box predictor here has classification score, whether there is an object or not, and the bbox predictor. So basically here we have the different coordinates of the bbox if it exists, right? And there you go, you have your architecture that you have seen already. Everything here, I hope that you're already familiar with it. And there you go, you have the Mask RCNN architecture. So basically it's just convolutional neural networks followed by some, what is it called? ReLU activations, convolutions, ReLU, convolutions, ReLU. And then here we have the convolutional transpose 2D just to augment the size of the image, right? Now we will be doing the training. Here you will be seeing a lot of information about the training. So basically removed 0 images with no usable annotations. If you have any problems in your annotations, it's going to validate them first and then tell you how many of them were false or bad, right? And then he will be telling you some information about the training. Here you are starting the training. we already finished the training because we only did like 300 epochs, 300 iterations, as you have seen. You get the total loss, classification loss, bounding box regression loss, mask loss. All of these losses are here. For example, RPN loss, RPN loss. So this is for the classification loss of the RPN. Time, date time, I don't know what that is. Learning rate. So basically you have
you want to say like we have like regression loss separately for like the model itself and for RMP part.
Yes, just remember, what did we have? So basically, we have one output from the RPN, region proposal network, that gives you the bounding boxes, and we have another place that's giving us the bounding boxes. So basically, there are two losses, right? So it's the same loss, function, but they are two different values of the loss, right?
Okay.
Nice. Yes, and here you have the memory usage and the learning rate. How is it progressing? It's pretty well configured with stuff such as TensorFlow, so TensorBoard. So basically, you can easily visualize it here. It should load soon. Do we still have a lot of time, or we're running out of time? Sadly, since I made so many executions, you see the graphs are ugly, but yeah, anyway. Accuracy of fast RCNN. Loss bounding box regression, loss of accuracy, the loss of mask, all of the other different losses. There you go. You can see them here, visualize them. For inference and for testing, I really just want to show you guys this code. It's very simple. So we basically create a new, something called as default predictor. Remember that? We give it a score threshold for testing, which is 0.7. So basically, if the predictor, if the classifier says this is a balloon with 0.7 probability or higher, we take this box. If it doesn't, then we take less. We load the weights from here. Previously, we were loading the weights from the model zoo. Now we will load them from the local path, right? And this is just for sending the image through the predictor. According. Oh, nice. So we have some time. Nice. So basically, we have the outputs here, which are the output of the predictor on the image. And then we use the visualizer to visualize these outputs, right? There we go. It's not bad, huh? It's really not bad for just how many images did we use for training? 61.
61 images and only 300 iterations, and it's very good.
And it's already this good. Why is that? Because the images that we're using here are very similar in style to the images of ImageNet and the images that were used for pre-training. So basically, this is why you get very good results. If you're going to be using it on medical images, or you're going to be using it on stuff such as, I don't know, like, for example, I work with historical data and stuff like that. Usually the performance decreases a little bit, and you would need to, what is it called? Have a bit more data and train a bit longer. But now let's come to the evaluator. So basically, we will be creating the evaluator, giving it what is the evaluation dataset catalog, and basically tell him what are the evaluations that we want. So we want to evaluate based on bounding box and the output of segmentation, since our model is mask RCNN, right? And basically, just we build the thingy and start classifying. Again, if you, this is just for visual purposes. If you want to use the inference values, for example, as a dictionary, and later on send these values in your own interface, or I don't know, save them in Comet, for example, or if you are working with Kubeflow later on, you'll be saving them in the Kubeflow's metric system. Yes, so basically here is the output of the model. We get the different average precisions at different IOUs with the different sizes of the objects. So basically here we have all objects. Here we have only the small objects. Here we have the medium objects and the large objects. These things can be found on, what is it called? The threshold for what is a small, medium, and large object can be found on the GitHub repo of Detectron, but it's usually pretty generic, right? And there you go. So you have the average precisions here, very useful. Average recalls here are also very useful. And you can go ahead and make the calculations. Remember those? To make the mean, average, precision, and stuff like that. Here are the average precisions of different at different places. So this is the average precision in general. This is average precision with 50, so 0.5. Average precision of 75. Average precision on the small images, small objects. Average precision on medium-sized objects, and average precision on large objects. Whew. And then we have, I think we should have the, yeah. Okay, so average recall, area all. Which one of them? Where's the recall? Ah, yes, yeah. So suddenly this one doesn't give you the F1 score. So basically, F1 score should be calculated manually. If I remember well, YOLO v5 and YOLO v4, they also give you the values for the F1 score and the precision and recall. So different models give you different default evaluators, but you can evaluate by your own and create your own functions. Just a small example on how to use the other types of models. So remember previously, we were using the Musk RCNN library, right? The Musk RCNN config file, I mean, and now we have the key point RCNN file. So here you see we are detecting the different key points of the body of a human being, and you can use it directly. It's pretty well trained. So if you would like to be doing stuff such as, I don't know, for your final project, you want to detect yoga poses, you can just use this one and evaluate whether the person did the good yoga pose. And this is actually a product that's out there that uses Keypoint RCNN and just evaluates how your yoga poses are, tells you should bend a bit more, you should do something like that. So basically, this is a product that you can guys build. This is another example for how you can build panoptic segmentation, and you can see that using them, it only takes like a couple of lines of code, right? So basically, you get the config file of this model that you want, you get the pre-trained weights of that model, and then you basically just run it on the image. That's it. It's very simple, huh?
Very simple. But the only hardest part of this and previous models is just to set up them.
It's what?
Set up them correctly.
To set them up correctly, yes. So basically, if you would like to install Detectron on your own machine, things are going to be a bit more difficult than this one. So basically, when I installed it on our server, it took me like a day. Yeah, so just setting up PyTorch and setting up Detectron, installing Darknet, and these things will be one of the most difficult tasks you'll be doing. Because once you have them installed, everything is running correctly. You already know how to change the convex. You already know how to fix the data set and change the formats. And as you can see, the training, evaluation, and just using is very, very simple. So just 3 lines of code in Python and you are done. I will try to get and show you a little bit on YOLO v5, right? Very quickly. I wanted to do a section where we speak about what's new in YOLO v4 and YOLO v5, but I guess wrong. Let me see what you guys are seeing. Do you guys have any questions so far?
Why and when we stopped the support for Detectron 2?
I have no idea. They actually did this thingy just 3 days ago. Like I realized, like I was using it, and then I just ran the same code, and patati, it's no longer there. I checked their GitHub repo, and they removed everything related to Colab inside their GitHub repo. I don't know why they did that. Bad people. Yes. If you'd like to train any object detection model that you already have you heard of, probably there is a good started file or Colab notebook provided by RoboFlow. So RoboFlow is like a website for making annotations for object detection. And just to increase the use of their website, they provided these Colab links for all different types of models. So basically, all you have to do is just open their model for YOLO v5, use their type of data. So basically, download the data from their website and basically just run everything the same way. And doesn't matter what data set you're using, this Colab link will fix itself basically to that data set. So in this example, we'll be running the YOLO v5 model, which is built on PyTorch, and it's provided to us by a team called Ultralytics, right? So basically, they are a company for artificial intelligence. So it's an artificial intelligence agency, and basically they proposed to give this YOLO v5 architecture. YOLO v5 is not an improvement over YOLO v4. So basically, it's an improvement over YOLO v3. So basically, YOLO v1 improves YOLO v2. So YOLO v2 improves YOLO v1. YOLO v3 improves YOLO v2. And then the real YOLO family stops at YOLO v3. And then every person starts making its own version of YOLO. So now we have PP YOLO by some Chinese laboratory. We have YOLO v4, which is an improvement of YOLO v3 also, and we have YOLO v5, which is an improvement of YOLO v3.
Officially, YOLO v4 is like created by the pupils of original author of YOLO v3, like the students of this professor.
Yeah,
that's why like it's.
Yeah, and it's the only one that's actually a paper. YOLO v5 is not a paper. It's not the paper that was peer reviewed, so it's just a code, right? Whereas YOLO v4, it's a paper, it's something that was peer reviewed, and basically there's scientific consensus on it. So again, we just download the data, right? In this case, as you can see, we don't have a lot of make files and stuff like that. So basically, it's just installing the requirements, and there you go, you have it. It's just Python code, right? Python code, right, written in PyTorch.
May I send this notebook in the chat, please?
In the chat, yeah, but you know.
Just send this.
Yes. Sure. So again, as there are different data formats, let me close this one. Remember, we said there are different data formats. For example, for Detectron, there is different format for YOLO v4, and there is a different format for YOLO v5. We will take a look at this format today for YOLO v5, and for your homework, basically what I will be asking you to do is you will take the format of YOLO v4, convert it into the format of Detectron. Here we go. We just downloaded our data. The data comes with this data.yaml file. Data.yaml file contains this array of names of the classes. It contains the number of classes that you have, and contains the directory of images for training and the directory for images of testing. You have guessed that you can see in here, for example, the let's go for the validation, right? So here we have the images in a separate folder, the labels or the annotations in another folder, but they still follow the same architecture as YOLO v4. So it's not the same data, same folder structure, but it's the same structure for the TXT files. So basically the class and then the location of the object. Let's close these. How do I close this? Close. Nice. Tick. I think this is completely useless. Let me check it. This is probably just to give you what are the names of the classes. Let me check. Oh no, it's well, it's a format for saving the labels. Okay, got you. So basically, this is a format for saving the labels. Cool. The main way is definitely to put the labels in TXT files inside a folder called labels. Later on, we will be changing this one. So basically, this is the model 5S of YAML of YOLO v5. So basically, YOLO v5 also has different levels or different model architectures. The YOLO v4 comes with X, S, and so it comes with X and tiny, whereas the YOLO v5 comes with the S, M, X, and L, right? So there are 4 levels of, let me check. Yep, here they are. So there is YOLO v5L, YOLO v5M, S, and X. X is the biggest, large is L, medium is M, and small is S, right? What you should be changing here again, so basically it's the number of classes, remember that. And I think that's it, right? Yeah, I think that's it. The rest is configured for you guys. And there you go, you start the training. So now it's Python code. You can either do it like this by running a Python trained or something, or you can wrap it inside of your own function, do the training in, what is it called? Inside PyCharm or something like that. Number of epochs. So this is this image size, right? A batch, number of epochs, the data. This is the data.yaml. Remember data.yaml, which contains this information. Where is the data training? Where is the validation data? And what are the different names of the classes? And here we have the config file, and we have the weights file. We don't specify any weights, meaning that the YOLO v5 script, training script, let's look at it, will be looking for the file for pre-trained weights on its own repository. Yes, so basically let's look at it. Where is it? I think it's before, right? It's in the main. A little bit before. Here, yes. Yep, there we go. So here we send it the weights. Where's the weights? There's the weights. So default is a YOLO v5 SPT. If you don't give it anything, it will take this one. Usually, if you don't give it, it will infer it from the config file. I will just want to look for it. So can you guys find something said model equals? Model equals. And it doesn't search inside these text files. Anyway, I think I have checked it before. Maybe it's here. Commons. Download. No. There should be code here for downloading the model. Not sure where it is. It's called download weights. Ah, there it is. Attempt, no. So it's here, definitely here. And then let's look for it.
Like model equal symbol.
Yep. So yep, there we go. Again, so basically using this command of running the training file, training script in here, we will be doing the training. While the training is happening, you're going to be seeing lots of information about the losses. So first you will be seeing the architecture of the model, right? Let's look at it. And then it will be reading. Let me check. Where did it? Code is out of date. Okay. Scanning, 0 missing, corrupted. It will tell you if there are some files which are corrupted. Caching, scanning, so it read the it read the validation data also. Nice, uses the anchors by default. And I think that's all. Yeah, and then just the loss functions and stuff here. You also get the MAPs. I think it's going to take a lot of time to train, but then again, the same thing for visualization. You can see it here in, what is it called? In TensorBoard. For running your training data. Let me see. Running inference. Yes, so basically Python detect, we give it the weights. So this is where the area was, the weights were located, and basically the image that we want. Let me check if he already created this XP file. Runs, train, nice. So we're already having the first weights that we have so far. Let's check, there we go, some example images. So basically this is the examples that he is running the testing on, right? And this is the distribution of your labels. And these are the hyperparameters used for the training. So this is what you get in here. Usually after you start doing the validation, you will have another folder here called validation, and it will have a results.json file, I think. Yeah, the results.txt. Okay, sorry. It will have a results.txt file that you can easily just parse through and get all the data or the information about the training that's happening. Do you guys have any questions so far?
One very important question.
Yes.
Why YOLO v5? Is like I was looking to a really big amount of time in YOLO family, in YOLO version 4. Actually, the comparison between YOLO v4 and YOLO v5, and actually we said YOLO v5 is absolutely insufficient and uncomparable to YOLO v4. Why will we spend our attention and time for YOLO v5 in this case?
That's a good question, but I would say that the comparison made between YOLO v4 and YOLO v5 was not very objective. I ran the Alexei IB model and hyperparameter tuned it on several projects. And some cases, YOLO v5s model outperforms the YOLO v4 model, even the YOLO v4 scaled, which was like supposed to be the best YOLO v4 version out there. And even Alexei IB himself made the comparison between YOLO v4 scaled and YOLO v5. Well, through what I've seen, YOLO v5 still outperforms YOLO v4 in different scenarios. So it's still very useful model, to be honest.
Okay.
Yeah. So don't. Yeah, I know that there are many comparisons right now, especially inside the Alexei IB repository, and since he is the guy who made YOLO v4s, he made lots of different comparisons between the two models, and in all of his comparisons, YOLO v4 is best. But YOLO v5 is, from my point of view, still a very good architecture to use. Let's check what he puts, right? Let me check. Help me out. What's the name? Alexei IB. Medium. Yeah. So this YOLO v4 CSP and P5s, he says that they are much better than. So these are the architectures. I want to see the README. No, not here. Where is his README? We made a comparison between them.
You are not on GitHub.
Da. I should have it here. Here it is. I don't think there is the YOLO v5 here. Yeah, it's not this comparison. He made another comparison after this one, where he spoke about the difference between YOLO v4 versus YOLO v5. And he says that his model is best.
I'm like not lying. I like search for many comparisons and many life scenarios, many of them like from third parties, which are not ours.
1 second, guys.
Okay.
Nice. Can you guys hear me again?
Yes, I can.
Хорошо. So I just found one good comparison here about them, but I couldn't find what he used as comparison. I will send you guys links later on for this one. For now, I think it's good to know both models exist. You have already seen how, what is it called? YOLO v4 is being trained. You can easily swiftly change between YOLO v4 scaled and YOLO v4. And for example, YOLO v4 tiny, the differences are not that much in the config file or the changes of the config file. So it's important to get at least one view of YOLO v4 and YOLO v5. Now, whether you will be using this one or the other, this is a decision that you will be making on your own. Yeah. Do you guys have other questions?
May in this case, please provide some examples when maybe next time about where YOLO 5 is better than YOLO 4.
There isn't really something like that. You can't really say this YOLO v5 is better on small objects or YOLO v5 is better on large objects. It's the comparison can be done on several benchmarks, but to be honest, if you want to build something for your own, you're always going to have to compare them one by one.
Okay.
So basically, on every time you will be building your models or training, evaluating, you should create. Yes, here it is. So you should basically create your own values, right? So basically, you should create your own new model v4, evaluate it, create model v5, and evaluate it, create them or in different sizes. So basically the YOLO v4S, YOLO v4, YOLO v4 tiny 3L, all of them, try them, all of them, because it really doesn't take a lot of time to do the coding, right? For you, it's just changing the config file, and it's very simple. So it shouldn't be something that scares you or stops you. Just running on Colab a few times, you run this, run this, run this, run this, and compare it on your own. You guys get it?
Yes, thank you very much.
Thank you. So do you guys have any other questions?
What will you do next time?
Next time we will be seeing, what is it called? So next time we will see first the paper for YOLO v4, the paper for YOLO v5. We will see what is object tracking and how can we implement it. We will see also image segmentation. So we've already seen what is bounding. So basically the mask RCNN architecture, which does the segmentation. On the next lecture, we will see it in more detail. We will speak about different algorithms that exist for segmentation. And then we will have a lab of segmentations. And hopefully, if we can manage to finish these in the first day of Friday, we will get to GANs and facial recognition on Saturday or Sunday. The next day, basically. Yeah.
Okay.
Again, just a quick reminder. The quiz will be done after a small recap of the lectures. And I think we are getting close to the first midterm or to your only midterm. So midterm exam. So I think after this lecture, can we just have a small conversation right now about how would you guys like to do the midterm? It's going to be very easy. It's going to be open book, but you will be doing it inside a classroom with some supervision of a professor. You will have access to your laptops. You will have access to your notebooks. And basically, yes, answer the question and scan the picture and send it to me on either on Moodle or, for example, directly on Telegram.
I feel maybe we can make the votes on, like I said, all the like possible variants. But from my point of view, yes, I think in the classroom with your friend and actually like send you directly to Telegram for your convenience.
Yeah, I think it's a very easy way. All of you guys will be able to first get access to all the lecture slides or anything you would like to use, for example, your lecture notes. And at the same time, we will be making sure that you're not cheating on each other. Again, the final and the midterms are going to be very easy. The same style of questions that we have in the quiz, but usually a bit longer. That's it. So you can finish it easily in 30 minutes. But we will be giving you 1 hour and 20, or let's say 1 hour and 15 minutes for the midterm, and then just 15 minutes for the taking the pictures and making sure that everything is very clear, and then sending it to me on Telegram or uploading them on Moodle. What do you guys think?
Yeah, I think it's fine, but it will be like theoretical questions only, not coding, right?
Of course, I will not ask you to code on paper, but
okay.
maybe I don't think I will be doing a what is it called, a practical exam. So basically, where I will give you a Colab link and just fill in the blanks. I would rather just see how you guys do on the homeworks, right?
Yes, I think homeworks and final project is okay for like practicing at the code, and actually like quizzes and midterms for theoretical.
хорошо. So if you guys have any other questions, please feel free to ask me on Telegram. For now, I think that's it. I think we already passed the time. Oh, we passed it largely. So thank you guys for assisting. I will upload the recordings of today and yesterday and upload the links for the different files.
Okay.
Thank you so much.
See you guys.
Thank you.
Thank you
Have
very
a great
much.
day.
Thank you.
Thanks.
Bye-bye.
Bye.
Bye-bye. See you guys. Thank you.
Bye bye.
Bye-bye.